All right, for today's deep dive, we're jumping into block recurrent dynamics in VTs. And this paper has some massive implications for how we understand and maybe how we build our biggest foundational vision transformer.
It really does. The big idea is this. We see these massive VATs, like Dyno V2, with dozens and dozens of unique layers, and we just assume they're exponentially complex. But what this research shows is that they have this profound underlying simplicity.
So all that deep computation, all that apparent complexity can be accurately rewritten using just a tiny number of reusable blocks that are just applied over and over again.
Exactly. That's the Block-Recurrent Hypothesis, or BRH. And the proof they came up with is just astonishing. They built a model called Raptor that's recurrent approximations to phase-structured transformers.
And Raptor, using only 2 or 3 of these distinct recurrent blocks instead of the original 24 unique layers, managed to get back between 96 and 98% of the classification accuracy of the huge Dyno V2 model on ImageNet.
And this is the crucial part. They did it at the exact same computational cost. It's ISO FLOPs.
So we're not talking about compression or a smaller model. We are talking about finding the fundamental, simplified program that the VIT is actually running all along.
Right. And that discovery moves us from just guessing at architectures straight into what they call dynamical interpretability. We can finally treat the depth of a VIT not just as a sequence of layers, but as a robust, discrete, time-dynamical flow.
It feels like the ultimate shortcut to mechanistic understanding, which is why this is so critical if you're working on safety or stability or just efficiency in these big models.
Okay, let's unpack this illusion of complexity then.
Yeah.
VITs are just dominant in vision, but their depth, 12, 18, 24 layers, it makes understanding the mechanism incredibly hard.
Yeah, we know they work, but we don't really know why they settle on the representations they do. It's a bit of a black box.
That's right. And the authors started with a hunch, really, based on residual connections. That structure itself suggests an implicit link to dynamical systems, kind of hinting that layers might not be totally unique, even if their parameters are different.
So the first step was just to look at the data, right? An empirical observation across a bunch of different VTs, Dyna V2, SIGLIP, all different scales.
Exactly. They looked at the layer-to-layer representational similarity matrices. So basically asking, how similar is the output of layer 5 to layer 6 and so on. And what just kept popping up consistently was this really striking block diagonal structure.
Right. So layers right next to each other are super similar, forming these blocks. But then you cross a boundary into the next block, and bam, the similarity just drops off a cliff.
It looks like a staircase with just 3 or 4 really long steps, even though the architecture makes you think there should be 24 individual little stairs.
But this is where you have to be careful, I imagine. Just because 2 layers look similar doesn't automatically mean they're functionally the same.
That's the critical question. Does this phase structure actually reflect genuinely reusable computation? And that's the gap the block-recurrent hypothesis had to fill.
Okay, so the BRH formalizes this. It says we can replace this deep L-layer VIT with computation that uses just a few blocks, let's say K blocks, where K is way smaller than L, and these blocks are just applied recurrently.
And the constraints on that are so important. The recurrent model has to reproduce the entire internal computational path of the original VIT, and it has to do it at the same speed, ISO FLOPs.
Which stops you from just finding some trivial compression trick. You have to capture the functional core of the original model.
Exactly. Which brings us to Raptor. It's one thing to hypothesize this, but building that simple recurrent machine, that's the acid test.
It really is. And it's a huge challenge, right? Because
Right.
training recurrent models to mimic these deep feed-forward paths is notoriously difficult.
Yeah, think about it. In a normal VIT, if layer 5 makes a tiny mistake, layer 6 can just fix it. No big deal.
But in a recurrent model, if block 1 makes a tiny error on its first pass, that error gets fed back into the same block again and again and again.
It compounds. The error accumulation leads to divergence. The rollouts just drift wildly off course, so they couldn't just use standard distillation that only looks at the final output. They needed Raptor to match the teacher's internal state at every single step.
So how did they get around that instability, especially with a model as big as Dyno V2?
They came up with this really clever 2-stage approach called hybrid training. The best analogy is teaching a kid to ride a bike. You start with training wheels, and then you gradually lift them up.
The training wheels here being teacher forcing?
Precisely. In stage 1, they used a mix of 2 losses. One was the teacher forcing, TF loss. That's the safety net. Every single time Raptor ran a block, They'd reset its input to the ground truth activation from the original ViT.
Okay, so that prevents the rollouts from drifting too far off. But if you only did that, Raptor would never learn to handle its own mistakes, right? It would always need the teacher to correct it.
That's the classic train-test mismatch problem. So they also combined it with an autoregressive, AR loss, where Raptor had to generate the next state based only on its own previous output.
And the key was that they gradually weaned it off the teacher forcing.
Yep. They started with a balance between the two losses, and then over the first 5 epochs, they slowly annealed the weight of the teacher forcing loss down to 0, forcing Raptor to rely more and more on its own predictions.
And then stage 2 is where the training wheels come off for good.
Stage 2 is pure inference simulation. All the blocks are connected end-to-end, and it's trained using only the autoregressive loss. This is absolutely crucial. It forces the recurrent blocks to learn how to coordinate, to be self-consistent across the entire depth, just like they would have to be at inference time.
But hold on, before they even started training, how did they know where to put the boundaries between the blocks? I mean, a ViT has 12 or 24 layers. How did they decide to split it into, say, 3 recurrent blocks?
They basically operationalized that blocky structure they saw in the similarity matrices. They framed the problem as a weighted max-cut problem and solved it with dynamic programming.
Okay, that sounds a little dense. What does it mean intuitively?
It just means they were systematically looking for the best possible chapter breaks in the ViTs computation. The algorithm found the partitions that maximize similarity within a block while minimizing the similarity across any 2 block boundaries. They let the data tell them where the natural breaks were.
And the results proved that this structural similarity was actually functionally relevant.
Absolutely. The partitions from the max-cut algorithm blew the random or just contiguous partitions out of the water on smaller benchmarks. It proved that representational similarity really is predictive of functional reuse. But, the foundation model results are what really seal the deal.
Right, that's the Dyno V2 result. With just 2 recurrent blocks, Raptor gets to 96.1% of the teacher's accuracy. With 3 blocks, it hits 98.2%.
And that 98.2% recovery meant it got an 83% top 1 accuracy, which actually exceeds the performance of the smaller Dyno V2 VT small model.
Wait, hang on. Let's just sit with that for a second. We're talking about replacing dozens of unique, independently trained layers with just 2 or 3 simple, reusable tools. And you only lose, less than 2% of the performance? That is structurally profound.
It is. And the ablations they ran proved how important that careful 2-stage training was. If they trained only with teacher forcing so, leaving the training wheels on the whole time, the model completely collapsed. It got like 3.9% accuracy.
Wow.
That second stage, the end-to-end autoregressive fine-tuning where the blocks learned to self-coordinate, was absolutely critical.
The implication for model simplicity here is just massive. The fact that a top-tier ViT can be boiled down to this compact, recurrent program means it has what's called low-level complexity.
And this is a huge theoretical takeaway. It suggests the algorithmic description of these foundation models is way, way simpler than their parameter count would suggest. The 24-layer ViT is, algorithmically, just running a short, compact, recurrent program.
Complexity is an illusion. It seems like successful networks find and reuse a really minimal set of computational tools.
Okay, so we've established that this recurrence emerges, and we've proved we can build a simple model, Raptor, that mimics it. So the next logical question has to be, mechanistically, why? Why does the network prefer this simplicity? What causes this bias during training?
The main thing they pointed to was regularization, right? Specifically stochastic depth.
Yes. Stochastic depth is usually just thought of as this trick to prevent overfitting by randomly dropping out layers during training.
But what you're saying is it's not just a guardrail. It's actively sculpting the network into this recurrent structure.
Precisely. They found a strong linear correlation. As they increased the stochastic depth dropout probability, the layer-to-layer similarity went up dramatically. The layers were literally forced to become more similar, more interchangeable.
That's so counterintuitive but brilliant. By forcing the network to be robust even when a layer is missing, you're basically encouraging the other layers to become functionally redundant, to become reusable.
And that increased similarity directly correlated with better reconstruction by Raptor. So the more regularization, the more recurrent the teacher ViT became, and the easier it was for Raptor to learn that underlying simple program.
So recurrence is a feature of a well-regularized network, a normative state.
Right. They even found that once the teacher ViT started to overfit, Raptor's accuracy in reconstructing it just plummeted.
And to really nail down that these blocks were functionally reusable, they did that satisfying causal intervention. They just took the trained Dyno V2 and started swapping layers around.
And the results were so clear. If you swap layers within one of the blocks they identified, an intra-block swap accuracy stayed high. The layers were truly functionally interchangeable.
But if you swapped layers between two different blocks,
The model collapsed. An intra-block swap completely broke it. The different phases are doing functionally unique things, but the layers inside a single phase are basically computational clones.
okay, so with the BRH confirmed and Raptor working, we can now pivot. We can start using the tools of dynamical interpretability. Because if the ViTs depth is really just iterations of a recurrent program, we can analyze it like a chaotic system or a feedback loop.
We treat the depth dimension as a discrete time flow. And the first key finding is about directional convergence. They notice feature norms just grow with depth, which kind of complicates things, so they focused only on the unit sphere, just the direction of the tokens.
And what they saw is that the tokens start moving around, but eventually their trajectories all collapse. They approach a directional fixed point.
It's like the trajectory is locking onto the final correct answer. The cosine similarity to the final state just saturates near 1.
And geometrically, these paths fall into these compact, class-dependent angular basins. So all the cat images flow towards one specific angle in feature space, and all the dog images flow towards another. They're like attractors.
And the system is incredibly stable. If they injected a little bit of noise into a token's direction halfway through, the trajectory would immediately bend back toward the unperturbed path. That's real evidence of local self-correction.
It shows that the flow is really stable, really contractive on the sphere, which, speaks to the reliability and fault tolerance we see in these big models.
But not all the tokens behaved the same way. The second finding was about token-specific dynamics and punctuated transitions.
Right. The different types, the CLS token for the final classification, the patch tokens for local features, they all follow different rules.
Exactly. The CLS token is pretty slow at first, just kind of consolidating information, but then it has these sharp late-stage reorientations. That seems to be where the global knowledge crystallizes. The patch tokens move at more of an intermediate speed.
But the coolest part is how all of this aligns perfectly with the recurrence hypothesis we started with.
Yes, the angular speed statistics, so how fast the tokens are changing direction, they show these abrupt changes that line up precisely with the block boundaries that the max-cut algorithm found.
So each recurrent phase has its own stable dynamic, its own continuous flow. And then it hits a block boundary, gets reset, and starts a new phase with a new dynamic.
A beautifully punctuated process. It's more validation that those block divisions are functionally real.
Okay, the final finding, and from a complexity standpoint, this is maybe the most mind-blowing, is about low-rank collective motion. What actually happens to the dimensionality of the computation as you get deeper into the network?
This is where that illusion of complexity just completely shatters. In the later layers, the stable rank and the effective rank of the layer-to-layer update matrix they collapse dramatically.
What kind of numbers are we talking about here? How restricted does it get?
The rank collapses to values near 6.
6, that is absolutely tiny. The feature space is, 768 or 124 dimensions? And the model is doing its critical work on a 6-dimensional manifold.
It's highly, highly restricted. The network goes from operating in this huge high-dimensional space to confining all its motion to this narrow, low-dimensional subspace.
Wow.
And at the same time, they found that the patch token coherence shoots up. All the local tokens start moving in this highly aligned collective motion. It's like a mean field effect where they're all working towards a shared goal within that tiny subspace.
And they confirmed this with dynamic mode decomposition, right? Which showed that the important modes were mostly angular and that the CLS token had the longest computational memory.
It's the ultimate synthesis of the whole idea. The network isn't solving the problem by creating 24 independent high-dimensional functions. It finds a compact recurrent structure, and then in the final stages, that structure collapses the entire computation into this nearly trivial 6-dimensional flow.
So for all of us who are building, interpreting, and trying to certify the safety of these huge models, what's the most encouraging takeaway here?
I think the key discovery is the recurrence-induced simplicity bias. It seems that high-performing ViTs fundamentally learn to reuse a compact set of computational tools. And this structural regularity turns the apparent complexity of a 24-layer model into a tractable 2- or 3-step dynamical system.
Right. If complexity is an illusion, it means we actually have a manageable path toward mechanistic understanding.
It gives us a handle. Instead of trying to analyze thousands of unique connections across 24 separate layers, we can just focus on characterizing the dynamics of 2 or 3 functional blocks. That is an immensely more tractable problem for interpretability researchers.
This work really offers an incredibly encouraging perspective. The fact that the model converges to this compact recurrent program suggests that by using these tools from dynamical systems, we have a much more principled way in.
The structural regularity points to this broader, really intriguing principle. In deep learning, recurrence finds a way.
And if you want to explore these emergent dynamics yourself, the authors have provided a public implementation of the Raptor framework. You can find it by searching for Raptor at the Kempner Institute's GitHub page. You can now treat that complex ViT depth as a flow, not just a black box.